Hello, this is Simba Bright Summer, and I'm going to be taking us through taking you through graph-based contrastive learning for predicting and detecting Alzheimer's disease and frontotemporal dementia, together with my group mate Kaiwa Joshua Magazine. So we have our contents for our presentation, starting with introduction and all the way to the references, sorry, the acknowledgement. So first and foremost, we have the background and introduction. So our graph theory. So we are proposing use of graph theory to detect to analyze brain connectivity, and with this we are going to leverage the use of EEG signals, and these signals are non-invasive and they are cost effective. Non-invasive, we mean they are it doesn't require the use of traditional methods where you're going to have to operate a person to be able to to be able to detect the diseases that we are in search for, or to speak with the person and hear what they have to say, and then based on those traditional methods to make assumptions. No, we're actually using EEG data, and then we are going to analyze the brain activity to be able to come up with the results. Then we are using graph neural networks. Graph neural networks, this literally means use of neural data together with graph theory to be able to process data that we come up with. Then contrastive learning. The use of contrastive learning, this helps us to enhance features, the specific features that we are in search for while making the prediction or the detection. So we use contrastive learning to be able to enhance these features and look for the imbalance, like something that is abnormal out of the features. Then challenges, have the high dimensionality. This means there are many features, many attributes in the data, so becomes a bit difficult to come up with exactly to analyze exactly what you're looking for. Then the imbalance, the data sets are imbalanced, as we shall see. There's class imbalance, then the data is noisy. And then our goal is to come up with an interpretable graph neural network model. This model to be able to be understood by any person in the clinical sector. So early detection is our major goal. It's the reason for the project. Come up to detect AD or FTD early, because these diseases have no cure. So it's better to come up with the detection to know that, to analyze someone and get to know whether they have these diseases, given the changing behavior, changing language, memory loss, to see whether we can analyze and give treatment at an early stage. So related works, recent studies, literature review, we made research through journals, through PDFs all over the web, Google Scholar. We leveraged that to find out that this this has been done before, and therefore we are trying to create something that is a bit better, and sorry, something that is actually of using a new idea. Yeah. So as my colleague will mention, then EEG studies. So in the EEG studies, we are using spectral features. These features are what we use specifically to detect the disease. Then we are using contrastive learning. This helps in the feature enhancement. So to be able to know exactly what the exact features that we are in question. So the features that we need to be able to analyze a person. Then challenges. These challenges have been seen as well, especially the noise challenge, and then high dimensionality, and then models that are easily interpretable. That's our major goal. Then, and also the GNN explainer, because that would be used in researches to explain the model insights, how it works, the features it uses, the data it accepts. Problem statements. So we have our domain application problem and the computational problem. The domain application overlap. So usually the AD and FTD are they kind of have similar symptoms, so and saying. So it's a bit difficult to analyze both. Then non-invasive, as I talked about it. Then lack of interpretable models that are easily interpretable by clinical sector. Then computational problem, high dimension, I talked about it. EEG, high dimensionality of EEG, noise, artifacts, and class imbalance. We didn't have like classes that are the same all throughout. It was an imbalance. Then the GNN complexity, which is difficult to analyze in normal setting, then interpretability by the clinical sector. So objectives to determine classification accuracy, model EEG with GNNs, and then enhance interpretability using explainable AI, and to evaluate against baselines. Easy, easy differentiation of the disease together with the healthy person. So contribution, develop graph-based framework for EEG, built frequency-aware GNN, and then deployed novel XAI model techniques, and then evaluated GNN baselines. So this is our methodology, all the way to predicted results, GNN training, prediction, interpretability. Then the data description, we used 88 subjects, and then 62 electrodes per subject. Those are the frequency bands that were used in our analysis, and then the functional connectivity using nodes. Thank you.
My name is Kaiwa Jashabim Magezi, and I'm going to talk about the output results and discussions. So just below here, we have a group of graphs and visualizations that show the training loss and validation accuracy for each of the models that we implemented. One that stands out starkly is the hierarchical GNN, which is in the bottom left corner here, and it shows a very nice validation accuracy compared to the others. So continuing, we see the other set, the other four, because we implemented about 10 models. The remaining four. Our best model was the frequency aware GNN, which is in the bottom left corner still. Closely followed to it was the GCN2, which is on the bottom right. And this had a very good validation accuracy, which was our goal. This is a project that is in line with health, so accuracy is quite important to us. So then here we have just a summary of the results that we have from each of the models. We have the test accuracy, the precision, the recall, and the F1 score. So this goes through every single one of the models that I previously showed. There are visualizations for. Then here we have a table that is showing the confusion matrix for this particular project model that we chose, which is the frequency aware GNN, and it illustrates a bias for, let's say, the predicted AD. For example, this model is very likely to predict a frontotemporal dementia person as an AD person. Yes. So then, looking at the explainable AI results for the best model, we have this frequency band average histogram that is showing us that the alpha and the delta bands are the ones that are going to be considered widely. The gamma will not be considered as much, since it is almost always attributed to noise. And then the best channels that we are drawing importance from this project, we are using the 0 node and the 6th node, then the 17th node as well. Next, I'm going to explain the second best mode, which was the GCN2. And for this one, we can see the node feature attribution and node importance as shown in this in these two visualizations, and then the frequency band importance here on the right. And you can see that the alpha and the delta bands were the ones considered most, and just as well the gamma was suppressed because of its noise contributions. So then finally we shall look at the explainable AI results for the worst model, for which we used Lime. And here you can see that mostly the node 0 frequency bands are the ones that were highly highly considered, and this is problematic, especially for this particular algorithm model. So it will misclassify because of it's considering some bands over others, and yet they're basically the same. So for example, if you look at the node 0 alpha band here, very highly considered, and if you look at the node 1 alpha band, it is less considered compared to it, and that's the problem. Okay, and so we should also look at the model selection and the deployment. So we chose the frequency aware GNN because of its accuracy, and because it was considering the relevant frequency bands for its prediction. Then the XAI that we performed on our models was confirming the feature relevance. And this is the process we went through. We input the EEG data, we preprocessed it, we made inference from it, interpretability, then the output. Down here is just an illustration of what our UI looks like for the system. So here we have a demonstration of the developed product, and this is a video just going through that, takes us through the process of using the API that we created. And then just here to the right, we have an explanation for our IP assets. And basically, we have the frequency aware GNN, which is our novel architecture. We have a graph method that we used. Then we have the XAI method, which is a GNN explainer that we created, and then the software code. And these are basically our IP assets for this project. Hello, this is group 5, and this is a demonstration for our EEG classification app. So as you can see, you can upload your file here on our UI to the system, so you can browse the files on your desktop. And I'm going to use this subject one's data, EEG data, and I'll upload it. So the system is going to load the data. As you can see now, this takes quite a bit of time, so I'm going to pause the video and I will return when it is fully loaded. So yes, as you can see, the file is fully loaded and now the system is analyzing the data. As you can see at the bottom there, it's processing every chunk. It has divided this into about 600 epochs, so it's assessing every chunk and it's going to draw its prediction. This also takes quite a bit of time, so I'm going to pause the video here and I'll return when it is fully processed and the predictions are done. Yes, as you can see, the system has finished processing all the chunks and we have received our final prediction. As you can see, it lists here the prediction is that this is frontotemporal dementia. This person has frontotemporal dementia, and it has a confidence of 55.6%. And as you can see, it's also showing us prediction distribution between Alzheimer's and frontotemporal dementia. Let me see if I can move this here. Okay, so I can't move my screen face, but yes, so this is Alzheimer's and then this is frontotemporal dementia, and it scored highly on the frontotemporal dementia side, so that's why it has been classified there. It also goes on to give you, different methods for explainable, to explain how it came to that conclusion. As you can see, different representations for control, Alzheimer's disease patients, and frontotemporal dementia patients. And yeah, so all of this is what we were looking at, a system that makes predictions but also gives you insight into how it was able to make those predictions. As you can see here, so we have showing raw prediction data. You can choose to click on it, and when you click on it, it is going to it's going to run again, and it will basically give you even more well more insights. And as you can see up here, it's processing the chunk again all the way to 600, and so yeah, the process repeats. I will pause here and come back again when it is done. Yeah, so as mentioned earlier, so that portion of the system is still in improvement, but so it was taking quite a lot of time. I decided to pause it for the sake of this video being concise. And so yes, generally that's what we have been able to deploy. A system, you can upload your file, it will learn from the EEG data and make a prediction for the patient, but also be able to explain how it came to that conclusion. So yes, thank you very much for listening. This has been Group 5 demonstration. Then conclusions and limitations. So obviously the 48.89 accuracy from the frequency aware GNN, the XAI insights such as the alpha and beta bands being the most important. The fact that we used 62 electrodes. And the challenges were class imbalance and obviously the accuracy is still quite low. We have been able to achieve up to about 55% accuracy so far now. And the limitations were the class imbalance, the accuracy, and the small data set. And we have also put in place some solutions that we are looking to implement for this to improve these particular issues. Our next steps are just addressing the class imbalance, improving the accuracy, expanding our dataset, creating a multimodal sort of system which can implement MRIs, and also we're looking at considering real-time deployment for clinics, where someone can have their results in real time rather than having to get an EEG file after they have taken the test and then uploading it into the system. They can just test um, while their brainwaves are being read. And like to acknowledge our university first of all, our supervisor Mr. Galiwango for helping with this project, the Unipod team for helping us identify our IP assets, our dataset provider which was Open Neuro, and lastly myself and my group mate Simba Bright Samuel. Thank you for listening.